I'm going to do a few problems, but I'm going to do them a little faster than I have been doing them just so you can see how these processes work. Okay, here we have a series RC circuit, and R is 100 ohms. Estimate C. So really what we're trying to do is we're trying to find that time constant, RC. And this, of course, the form of this is going to be I max times e to the negative t over tau. And the important thing to do on this estimate C, is this concept of e to the negative 1 equals about 0.368. So in other words, on this case, it's going to be the time constant, t equals tau, equals RC. Tau is what we call that time constant. When these two things are equal, it's going to be 36.8% of its initial value. Okay, I always think of it as the opposite. I always think of it as the 1 minus this is about 0.63. So 63% of the way to the final value from the start is tau. Okay, so 63%, 63%, come over here, and that's going to end up being our tau, or 0.36, 36% of that total. Well, if 5 squares is the total, then we're looking at about, this is 40, 36%. So, excuse me. So that would be tau. Let's say tau is about 1.8 seconds. RC, so 100 C equals 1.8, and C equals approximately 0.018 farads. Okay, so that's this understanding about what happens with the time constant. Now let's look at this one, and we're going to go pretty quickly on this. I'm not going to actually show numbers. I just want to show the approach for the solution. Then I'll do a different one that has this 99% business. Find the tau for the discharging capacitor. What we have to do there is we have to replace this with an equivalent resistance. Okay? And that's going to be, we're going to replace that with 1 over R parallel is 1 over 100 plus 1 over 200. Then that will be in series with the 100 ohm resistor. Then we have this, and then it's just the same process that we have for finding the time for 99% discharge. That would just be Q of that time is going to be Q max, and remember the Q max is going to be this voltage because it had been charged for a long time. So it's going to be that voltage times C. So it ends up being C times 20. Okay, so if we want this to be 0.01 times Q max is C20 times 1 minus e to the negative t over tau. So the Q max cancels, and we have 0.01 is 1 minus e to the negative t over tau. I'm not going to plug in all the numbers, but that's the approach, is replace that whole thing with one equivalent resistance and then just use our normal approach for doing RC circuits. Oh, and actually I forgot one thing. Little letters there, internal resistance. So I'd really have to do that, include that in there also. Let's not worry about that right now. At one time constant, find VC, V100, sketch graphs. Let's just do the sketching graphs. Okay. So the capacitor initially is charged up to 20 volts. I'm ignoring internal resistance right now. And that voltage, as it discharges, will go like that. Okay, I don't even know why I have this in here. It doesn't really affect the ultimate circumstance when you open that up. So that's the graph for VC. V of the 100 ohm resistor there, well, it's going to start at some, as soon as you open that up, there's a voltage across that, and we'd have to figure that out just from like a resistive network. So it would be this voltage divided by the R equivalent, and then we figure out how much voltage is across this 100 ohm just by I. It's going to be the same as the R equivalent current. So that current's going to come times 100. You end up with V100, and it's going to do that. VI100, it's going to have that exact same approach, because as soon as you open this up, current is going to flow through this equivalent. That's going to be the same as I100, right? Whatever goes through there has to go through that entire equivalent. And it's going to start out as soon as you open, charge is going to be flowing that way. So there's going to be your current, and it's going to decrease over time. Current always is going to end up decreasing over time in an RC circuit.